See in the notes for AP Calculus on the topic of functions. So let's refresh your memory on what a function is. It's a specific type of relation in which each independent variable, which oftentimes will be x or t, but really could be any variable, in the domain corresponds to one and only one dependent variable, oftentimes y, in the range. So in other words, for every x value or t value that's an independent variable that you substitute into the function, you only get one dependent variable out of it as a y-coordinate or whatever that's called. Then remember, the zeros of a function are the values of the independent variable, if any, that make the function equal to 0. Just like it sounds. Figuring out what makes the function 0. That's the name, zeros of a function. And graphically, they're really just like x-intercepts. And algebraically, they're found using the same technique as x-intercepts. The only difference is you set the function such as f of x equal to 0 rather than y, because in function notation, we use f of x or g of x or something like that in place of the y. So let's look at a couple examples, one algebraic and one graphical. So it says find the zeros of the function. Okay? So just like you would do for y-intercepts, to find the zero, so the x-intercepts, you normally let y equal 0, but in this case there's no y, you let f of x, which is in the place of y right there, equal to 0. So we got f of x equals 0, and then solve for x. So you can see the first thing we can do, since we have one side of the equation equal to 0, is to factor. And there's a GCF, you always look for GCF first, so 3 goes into 3 and 48 evenly. So you get 3, and then x to the 4th minus 3 times 16 gives you 48. Then we can keep factoring that. You can use difference of perfect squares factoring. What squared gives you x to the 4th? That would be x squared. You go first. What squared gives you 16? That would be 4. 1 is minus, and 1 is plus. And this factors a little bit further. You've got another difference of perfect squares, x squared minus 4. What squared gives you x squared? That would be x. This first one. What squared gives you 4? That would be 2. Again, 1 is minus, 1 is plus. But x squared plus 4, that's a sum of perfect squares. That does not factor any further. Okay, so now that's in completely factored form, we can say, well, in order for these factors to multiply to be 0, one of them has to be 0. Well, can the 3 be 0? No, 3 is never equal to 0, so that won't give us any answers for the zeros. So it could be the x minus 2 equal to 0, or the x plus 2 equal to 0, or the x squared plus 4 equal to 0. So when you add the 2 here, you get x equals 2. Subtract the 2 here, you get x equals negative 2. And on this one, if you try to solve it algebraically, it doesn't factor, so you can subtract the 4. But notice what your next step would be to take the square root of both sides, right? Get rid of that square. And when you do that, you can see that gives you a square root of a negative number, which is imaginary. And those imaginary zeros do not show up graphically, so they're not considered the zeros. We're just going to be dealing with the real zeros here. So the only zeros, real zeros we have are negative 2 and 2. So those are the two numbers that if you were going to plug those in for x, they would make the function equal to 0. Now let's look at it graphically. This is actually easier. When you have the graph, remember, letting y equal 0, f of x equal to 0, it's just the x-intercept. So to find the zero of the function, you can just look under graph right here, where the x-intercepts are. You can see there's an x-intercept of negative 2, at 0, and at 5. Okay. So 0, 0, negative 2, 0, 5. These are really, zeros of a function are really just another name for the x-intercept. Where is this function g of x equal to 0? What x values? It's at negative 2, 0, and 5. And then plug in the function would be a y value or a function value of 0. All right, let's take a look at something else about functions now. Let's look at function notation and composite functions. Okay. So function notation we looked at a little bit is when you have f of x or g of x, something written that way instead of a y. But if a number expression replaces an independent variable, that number expression should be substituted in the function for the independent variable. So the reason why it's often useful to write things in function notation is that it shows you, okay, this is our function, let's say f of x, and if you have f of 5, that means, shows you visually, you're replacing x with 5. Or if you have f of t minus 3, you're replacing x with t minus 3. So whatever's in the parentheses is what replaces the independent variable. That's what that's saying. But you can also have composite functions, which are really like functions inside of functions. Okay? So sometimes you'll see it written this way. Now, this looks kind of like fog of x, but that's not what it is. The way you say this is f of g of x. Okay? And the order is important because this shows us the one that comes second, that's the one that's being plugged into the one that comes first. So the easier way to write this, to work with, is actually like this. F of g of x. Okay, so this shows you visually g of x is inside f of x. It means the same thing, just two different ways of writing it. So this is called a composite of f with g. And just a refresher on the domain and range, we'll keep talking about this with functions. Domain, remember, refers to the set of all x's. Domain of f, the set of all x's. And in the domain of g, such that g of x is in the domain of f. Okay? So all these values you plug in here for x are in the domain of g, and then the values you get out for that become the domain of f, is what that's saying. So again, this is not fog, it's f of g of x, it's written this way, we saw that up here. This is not goff, it's g of f of x. Wait, same thing here. Notice the difference between these two, since g is written first, g is the function on the outside, f is being plugged into g rather than the other way around. And you may also see something, this is not phof, this means f of x. Okay? So this means the functions can sometimes be substituted into itself. Okay? And we'll see what that looks like as well. F of x. You're plugging the function into itself, replacing the x with what it is. So let's look at some examples now. Given a couple particular functions, f of x equals 3x plus 5, and g of x equals x squared plus x minus 12. We're going to find each of these based on those two functions. So the first one goes back to what we just did, find the zeros of g. So here's g, so we set it equal to 0. G of x equals 0, and solve this for x. Then you can see you can factor that. Factors of negative 12 that add up to be positive 1 would be negative 4, positive 4 and negative 3. Multiply to be negative 12, add up to be positive 1, and we can use a shortcut here since it's just kind of leading coefficient of 1. And then just set those equal to 0. If you set x plus 4 equal to 0, you get x equals negative 4. If you set x minus 3 equal to 0, you get x equals 3. So our solutions there would be x equals, our zeros would be negative 4 and 3. Now let's find f of g of 2. So we have g inside of f, but notice we also have a specific number there too. So the way you work these out is start on the inside and work your way out. So let's first find g of 2. So g of 2 means in this function g, wherever there's an x, we're going to replace it with 2. So instead of x there, it will be 2 squared plus, instead of x right there, we have a 2, minus 12. If we work that out, we get 2 squared is 4, plus 2 minus 12. That gives you 4 plus 2 is 6 minus 12, gives you negative 6. So that's what g of 2 is. So now we can replace this g of 2 with negative 6, because we just figured out that's what it equals. So then we'd have f of g of 2 we just figured out is negative 6. This goes back and replaces. So f of negative 6 now means we use the function f of x here, where there's an x, we replace it with negative 6. So it'll be 3, but then instead of x, instead of negative 6, And then we've got plus 5. 3 times negative 6 is negative 18. Plus 5 gives you negative 13. So that's what f of negative 6 is. So that's what f of g of negative 2, g of 2, sorry, is negative 13. All right, let's take a look at one that's written a little differently. In the other notation, this one is written as g of f of negative 2. So let's write it that way, g of f of negative 2. So again, just like we did here, on part B, we'll start on the inside and work our way out, except this time, the f is on the inside. So we'll start by finding f negative 2, whereas on this one, g was on the inside. So let's first find f of negative 2. We use the function f, and wherever there's an x, we replace it with negative 2. So that'd be 3 times negative 2 plus 5. 3 times negative 2 is negative 6. Plus 5 gives you negative 1. So that's what f of negative 2 is. So we can take f of negative 2, and now we know it equals negative 1. So we can replace that with negative 1 and substitute that into the function g. So g of negative 1, now we use the function g of x here, replace the x's with negative 1. So it'll be negative 1, make sure you put in parentheses, that whole thing is squared, and then minus 1 for x there, and then minus 12. Well, that gives you negative 1 squared is 1, minus 12. You can see the 1's cancel out. Just left with negative 12. So that'll be your answer, negative 12. So that's what g of f of negative 2 equals, negative 12. So those are a couple examples of composite functions with a specific number plugged in for x. But sometimes you'll have composite functions like d and e when it's just left as x. In this case, our answer is not going to be a specific number. So again, we start on the inside. In this case, f of x is what's on the inside, but there's not a number to plug in for x, it's just f of x. And what is f of x? Here it is. F of x is 3x plus 5. So let's replace it with what it is. F of x, we know, is 3x plus 5. And now, this may look a little weird if you haven't done these before, but g of 3x plus 5, just like when we had a number in there, whatever's in the parentheses, that's what replaces the x. So this x right here gets replaced by 3x plus 5, both places. So this would be 3x plus 5 squared plus 3x plus 5 minus 12. And then it's just a matter of simplifying this. You square that out, that's like taking 3x plus 5 times 3x plus 5. So that would give you 3x times 3x is 9x squared. Then you'd get 3x times 5 and another 3x times 5. Those are both 15x. 15x plus 15x is 30x. And then 5 times 5 is 25. And then don't forget we still have the 3x plus 5 minus 12. And now it's just a matter of combining like terms. There's nothing to combine with a 9x squared, so 9x squared. We've got 30x and 3x gives you 33x. And then 25 plus 5 is 30. Minus 12 gives you 18. So that is what g of f of x would equal. 9x squared plus 33x plus 18. Now let's look at the same two functions, but this one's f of g of x. So remember the way we can write this in a simpler way is this means the same as f on the outside of g of x. So similar to the last one, g of x, there's nothing being plugged into it, it's just g of x. So we just replace g of x with what it equals. There's not a specific number to plug in for x there. G of x is x squared plus x minus 12. So start on the inside again, work your way out. Okay. And then this says wherever there's an x, in this case just one place, and f, we replace that with x squared plus x minus 12. Whatever's in the parentheses replaces the independent variable. So we'll have 3 times, instead of x, substituting in x squared plus x minus 12. Right? And then just distribute that out. Gives us 3 times x squared, 3x squared, 3 times x, 3x, 3 times negative 12, negative 36. So notice, it doesn't make a difference here. F of g, same two functions, f and g. G of f of x was 9x squared plus 33x plus 18, but f of g of x was 3x squared plus 3x minus 36. So which functions inside does make a difference? You can see with those two. Now let's look at one of my single order, g of natural log of x. Well, we're only using one function here. We're not using f at all, but this just means, again, whatever's in the parentheses, just like the other ones. In this case, natural log of x, that's what replaces the x. So this would equal, here's g, instead of x, we'd have natural log of x squared plus, instead of the x there, replace that with natural log of x, and then minus 12. And there's nothing really we can do to simplify this. This is just one term, natural log of x squared is just natural log of x times natural log of x, not really anything you do that. And then plus natural log of x minus 12. So that is what g of natural log of x is. Okay, now let's take a look at some, instead of being given the actual functions, we're given a table of values. So let's use the table here. Sorry, I accidentally have an extra line in there. All right, let's use this table. Here's the, and we're given, right here, h of 0 is negative 3, h of 1 is negative 1, and h of 3 is 0. Okay, so we might need those on some of these problems. Define the following. So we're given the x values on the first row, and at those x values, we're given the y values for each function. So f of x, 12, 9, 7, and so on, and then for g of x, 5, 3, 0, and so on. And they correspond to the x values up here. So let's find f of g of negative 1. So we got to start on the inside again. And first, figure out what g of negative 1 is. So that'll be f of, well, g of negative 1, we're plugging in negative 1 for x, so let's find negative 1 for x, and then find g, let's see, that would be 0. So g of negative 1 is 0. Okay, place that. And now find f of 0. So this means we're plugging in 0 into f of x. So find where x is 0 right here. And find f of x is 5. So that's what f of g of negative 1 equals. Now we'll take a look at this a little more later here. But this h with a negative 1 out there, that's not an exponent. It actually means the inverse of h. Okay? Inverse function of h. So what an inverse function does, remember, is it reverses what the original function does. So basically we're trying to find where the original function, here this is the x value for the inverse, that would correspond to the y value for h of x. So if we look here, this is where x is 0, we want to look up here for h where y is 0. So we have h of 3 is 0, right? Right up here. And that means when you plug in 3 for x, you get 0 for y. This is a point on h. So since that's on h, remember the inverse, the x and y coordinates are switched. It reverses what the original function does. That means when you plug in 0 for the inverse, you get 3 out. X and y are switched, so that's the point that's on inverse function. And that means when you plug in 0 there, in the inverse you get 3. So the inverse of h of 0 is 3. All right, now let's take a look at h of f of 3. Remember the other way you could write this? H of f of 3. So let's first figure out what f of 3 is. Start on the inside again. And look at our table where x is 3 right here. Find what f is, it's 1. F of 3 is 1. And now we want to find h of 1, which are given right up here at the top. H of 1 is negative 1. So that's what h of f of 3 is. Now let's mix the composite with an inverse function. So first we want to find the inverse of g of negative 5. So the way you use this in a table, remember like here, is we're really looking for where the y-coordinate of the original function g is negative 5. So if we look at the y-coordinates of g, look for negative 5 along this bottom row. You can see right here, it's negative 5. That corresponds to an x value of 3. So basically that means that the point 3, 5 is on the original function g. So when you switch, negative 5. So when you switch it around, that means negative 5, 3 is the point on inverse of g. So that means when you plug in negative 5 in the inverse of g, you get 3. And then we find f of 3. So look in our table, where x is 3, we can see f is 1. So that's what f of g, the inverse of g of negative 5 is 1. Now let's look at a couple where we've got 3 functions inside. So this is f of g of negative 3. So again, let's start our work on the inside and work our way out. The innermost function here is g of negative 3. So initially I'm going to leave f alone on the outside and the g alone right here, and first figure out what g of negative 3 is using our table. So you can see at negative 3, g is 3. G of x is 3. So x is negative 3, g is 3. So that'd be 3 right there. And now I need to figure out what g of 3 is using the table. So when x is 3, g is negative 5. So g of 3 is negative 5. And now I need to find f of negative 5. Negative 5, f is 12. So that's what f of g of negative 3. So that's how you can have more than one function of the same function. Here we have 2 functions of g. Now let's look at the inverse of f of g of h of 0. Again, 3 functions we're using. But again, we're going to start on the inside and work our way out. So let's start by figuring out what h of 0 is. So we'll leave the functions on the outside alone, f of negative 1, and g, and figure out the h of 0 using the table here. When x is 0, h, whoops, it's not on the table, it's up here. H of 0 is negative 3, we're given right there. So that's negative 3. And then we can find g of negative 3. So negative 3, g is 3. And then it's the inverse of f of 3. So again, remember when you're looking at the inverse, rather than looking at this as the x value, you're really looking for where the y value of f is 3. So let's look at our table here for f of x, since we're working with the inverse. F of x, we can see the y value is 3 right there. And the corresponding x value is 1. So that tells us that on the original function, when x is 1, f is 3, that's the point on the original function f. So that means when you flip it around, this is the inverse, 3, 1 must be a point on the inverse of f. So that means when you plug in 3 into the inverse of f, you get 1. So that's what the inverse of f of g of h of 0 equals. Now let's take a look at what are called even and odd functions. And they're similar to what we talked about with symmetry, except We don't have a function that's symmetrical about the x-axis because that is not a function. If it's symmetrical about the x-axis, something like this, that would not be a function because it wouldn't pass the vertical line test. For one x value here, you'd have two different y values. So that's why we don't have any functions that are symmetrical about the x-axis, only about the y-axis or the origin. All right, now that we've dealt with that, let's take a look at these two here. So even functions are symmetrical about the y-axis. All right, so to see if a function is even, you replace x with x and see if the expression is the same. Now, hopefully that sounds familiar to you because that's the exact same test we use if we were to determine if something was symmetrical about the y-axis. We just have a different name for it, even, when we're dealing with functions. So what that means is, you can see it's symmetrical about the y-axis here, like a mirror across the y-axis. And that means when you change the x-coordinate to be the opposite, the y-coordinate should stay the same. Odd functions are symmetrical about the origin. Okay? So, odd function, you can see when you have x and y, some point on the function here, that's true. That means the point where x and y are both opposites, negative x and negative y, would also have to be a point on a function. So to figure out if the function's odd, you replace x with negative x and see if the expression is the opposite. The exact opposite. Or you could also replace x with negative x and f of x with negative x and see if it's the same. That would work too. Okay, so I'll show you guys a couple ways you can remember this in case you get mixed up which is which. One little mnemonic device, very simple and a little silly to help you remember this, is just look at the letters here. Y-axis goes with even. Okay? So y-axis even. Now we don't use this word nowadays in English, but if you read the Old English, you might see this phrase, ye old calculus textbook, something like that. Okay? And odd and origin, well, that's even simpler. They both start with the letter O. Put those next to each other, ooh, an odd function symmetrical about the origin. So, just an easy way to remember so you don't get those mixed up, which is which. I'll show you another way after we do these example problems too, just so you can see why they're called even and odd. All right, so show whether the functions are even, odd, or neither. It doesn't have to be symmetrical about the y-axis or origin. Sometimes it's neither one. So let's replace, on both of these, we replace x with negative x. So that just means wherever there's an x, you plug in a negative x. So that'd be negative x to the fourth plus 2 times negative x minus 2. And then simplify it to see if it's the same or the opposite or neither. Okay. So let's see. Negative x to the fourth, well, that's an even exponent, right? So we have negative 1 to an even exponent, it becomes positive, so that just makes it positive x to the fourth. 2 times negative x is negative 2x minus 2. All right, let's see if it's the same, first of all. It's the same, x to the fourth is the same, but negative 2x is the opposite, and negative 2 is the same. So it's definitely not the same. They're not all the same sign, they're not all the opposite sign of the original one, so it's not the same. Is it the opposite of the original one? See if it's symmetrical about the origin. Well, if it was the opposite, they would all have to be the opposite sign. This would have to be a negative x to the fourth, and this would have to be a positive 2. So it's not all the same, it's not all the opposite, so this one is neither. Because when we plugged in negative x, it turned out to be not the same as or opposite of f of x, the original function. All right, now let's take a look at the next one here. We've got h of x is x to the fourth over x squared minus 4. So let's plug in negative x, substitute negative x for x. You can see what happens. Negative x to the fourth, negative x squared minus 4. So if we simplify that, well, negative 1 to the fourth, that's an even exponent again. So that's just x to the fourth. Negative 1 squared, another even exponent, so that's just x squared minus 4. If you look back at the original one here, you can see it's exactly the same. So it's the same as the original, remember that's even. So that's what the y-axis. So this one is even. And that's because it's the same as the original one, h of x. Finally, let's look at f of x equals negative 2x cubed. Sorry, j of x equals negative 2x cubed plus 4x. So let's plug in negative x for x. Okay, negative 2 negative x cubed plus 4 times negative x. So that gives us negative x, to simplify. Well, negative 1 cubed, this is an odd exponent. So that's going to be a negative 1, but times the negative 2 out in the front makes it a positive 2. X cubed. And then 4 times negative x is negative 4x. So you can see, well, it's not the same as the original one. But look, negative 2x cubed became 2x cubed, positive 4x became negative 4x. So this one's the opposite of the original one. We plug negative x, and that's what makes it odd. So this is an odd function, symmetrical about the origin. And that's because I plugged in negative x for x, it turned out to be the opposite of j of x. Now, you might have already realized it, but let's take a look at why these are called even and odd. Okay? Now, it doesn't work for functions that are not polynomials necessarily, but the ones that just have are polynomials or just have x to some integer exponents, you can see why that works here. So notice the first one. Let's look at all the exponents. We have x to the fourth, x to the first. This one's even. This one's odd. And right here, there's no x. That's kind of like x to the 0. Now, what do you think? Is 0 an even or an odd number? Well, the way you can tell, the definition of even is it's evenly divisible by 2. Is 0 evenly divisible by 2? Sorry about that. Yes, it is. 0 divided by 2 is just 0. So this is an even exponent. So notice this one has a mix of even and odd exponents. That's why it ends up being neither. It's not exclusively one or the other. But this one you can see we've got x to the fourth. That's even. Exponent x squared is even. And this has got like invisible x to the 0 on it. Remember, anything to the 0 is just 1. So this has exclusively the even exponents, which is why it turned out to be even, symmetrical about the y-axis. Right? And then the final one, you can see the exponents. We've got x cubed, 3 is an odd number, and x to the first, another odd number exclusively. So it's got exclusively odd exponents, so it's an odd function. Okay? So that's another reason to see why they're called what they're called. But remember, this is not going to always work for all functions. Just looking at the exponents, you can have things that are in radical form. You can have things with fractional exponents. You can have trig functions, logarithmic functions. Other ones where just looking at the test would tell you without, well, you don't necessarily have exponents like this. Now let's take a look at domain and range. Okay? And particularly focusing on the domain here. So the domain, remember, is defined for functions to be the set of all values of the independent variable, often x or t, for which the function is defined. So which you actually get an answer, a real answer to it. So the range of a function, so that's like the input. The range of the function is like the output. This is the set of values of the dependent variable, oftentimes y, that a function can give you with all those exponents. And as it says on your notes, in calculus, we'll often write domains and ranges in interval notation. So this is inequality notation right here. So if the domain were between -1 and 7, not including -1 and including 7, the way you'd write that in interval notation would be like this. -1 with a parentheses because we're not including, 7 with a bracket because we are including. And just remember when you use interval notation, we never use a bracket for infinity or negative infinity. Because it's not a specific number you can include. You always use parentheses on infinity or negative infinity. All right, so to figure out the domain, which is all the possible x values, you look for restrictions on the independent variable, right? Or which is often x or it could be t or whatever your independent variable is. So the 3 common restrictions you want to make sure you're familiar with to look out for, right here. Denominators of fractions cannot be 0, right? Because you cannot divide by 0. Why can't we divide by 0? Well, what's 5 divided by 0? This is saying what times 0 gives you 5? Nothing, right? There's nothing we can multiply by 0 to give you 5. That's why this is called undefined. There is no defined answer to it. Another one that students sometimes think is undefined but actually has a different name to it is 0 divided by 0. This is saying what times 0 gives you 0. This time, it's not that there isn't an answer, it's that there's an infinite number of answers, right? 0 times 0 gives you 0, 1 times 0 gives you 0, negative 1/3 times 0 gives you 0. Okay, so there's an infinite number of answers, so this is called indeterminate. So you can't determine the answer. Where here, there is no answer, here you can't determine. But either way, dividing by 0 doesn't seem to make any sense. And we'll see later on in the year what that looks like graphically, how that impacts graphs. And we have something undefined or indeterminate. Okay. Now let's look at expressions inside radicals with an even root, like square roots. Those must be greater than or equal to 0. Square roots or fourth roots, and so on. The reason why is if they're not, you have like the square root of -4, then that causes you to get an imaginary answer. And we're just going to be dealing with real numbers in calculus, not imaginary numbers. So we're just looking for the domain of real, this is a set of real numbers, okay, that we can plug in. But odd roots are okay. You have an odd root, like the cube root of -8, that's just -2. You can have any kind of number inside of an odd root. So it's just the even roots you have to watch out for. And finally, the last common restriction you want to make sure you're familiar with and recognize is expressions inside logarithms must be greater than 0. Okay? So any kind of log, whether it's a common log or we'll deal mainly with natural logarithms, what's inside must be greater than 0. Let's say we have the log base 7 of x, for instance. Well, remember, this is saying 7 to what exponent gives you x, okay? Where the log equals the exponent. And notice whatever exponent we raise this to, if we raise it to a positive number, we're going to get a positive, right? 7 to the first, 7 to the second. If we raise it to the 0, we still get 1, positive number. If we raise it to a negative exponent, that doesn't make it negative, it just moves its denominator. So if you had 7 to the -2, that'd just be 1 over 7 squared, which is 1 over 49. So it's still a positive number. So when you raise a positive base like this, and logs always have positive bases, to any exponent, you always get a positive number, hence where the x's has to be positive, greater than 0. So keep those 3 things in mind as you look at whenever you're asked for the domain of a function. Because if you're asked for the domain and you're not given the graph, or it's not an easy one to graph, you want to know how to deal with those with just the algebraic expressions. So let's look at a few examples here. The range is a little trickier. You'll have to learn a little bit more calculus first to have all the tools we need to figure out the range. So let's just start with the domain. The domain of the following functions. Right? And notice most of these are ones that would be fairly more complicated to graph for what you know at this point. Maybe the h of x wouldn't be too bad, but the other ones are a little more complicated. So here, let's look for these 3 if we have any of these restrictions. Do we have any denominators of fractions cannot be 0? Yes, we do. We have denominator right there. So 2x cannot equal 0. And if you divide by 2, you get x does not equal 0. So that's one restriction. Can't divide by 0, so x can't be 0. Is there anything else that could affect the domain? Yes, there is. If we look at what's inside the square root there, that's an even root. Remember, when nothing's written there, it's like a visible 2 there. So remember we said expressions inside brackets with even roots must be greater than or equal to 0. Otherwise we get imaginary numbers. So x plus 5, that's inside there, in order to keep it from being imaginary, it has to be greater than or equal to 0. If you solve that by subtracting 5 from both sides, you get x is greater than or equal to negative 5. So probably, especially when you have more than one restriction, I'm going to write these in interval notation here. The easiest way to organize it is using our number line. So x cannot equal 0. So I'm going to put 0 down there. And I'm going to put an open circle to represent, okay, it can't be 0. And then it says x has to be greater than or equal to negative 5. So here's negative 5. Greater than or equal to, so it can equal negative 5. So I'll make that a solid circle. And greater than or equal to is this side, where the arrow's pointing there. And we're bypass 0 because we know x can't be 0, so it'd be like this. So that's a visual way of seeing what our domain would be. Putting those inequalities on the number. Now let's go ahead and write an interval notation. And with that number line, it's not going to be too hard to do that because we can just go from left to right. So going from the lowest to the highest, which interval notation always does, is starting with negative 5. That's our lowest x value in our domain. Notice it's included, we've got a closed circle because of the or equal to, so that would be with a bracket, comma, 0, we've got an open circle, so 0, we have to stop there, with a parentheses, because we're not including. And then in between, sometimes you can put commas, or I'm just going to use the union symbol. That's one interval, that's from negative 5 to 0, not including 0, including negative 5. And then it starts right after 0, so but not including it, so it'd be 0 with the parentheses. And then it keeps on going forever to the right. That takes you all the way to positive infinity. And remember, on infinity or negative infinity, you never use a bracket. It's not a specific number, so we'll use parentheses on that. So that would be our domain of this function in interval notation. Okay, let's take a look at g of x here. G of x, let's see if we have any of these restrictions. We have denominators cannot be 0. We do have a denominator. So let's make sure x squared minus x minus 12 does not equal 0. So to solve this one, you solve it just like you would if you were solving it with equal to 0. You factor it. So factors of negative 12 that add up to be negative 1 would be negative 4 and positive 3. Again, you can use the shortcut here since it's just got a 1 as a leading coefficient. And if you set those equal to 0, you get x, I'm sorry, not equal to 0. This time they both can't be 0. X does not equal 4. So that 4 would make this factor 0, and x does not equal negative 3. Because negative 3 would make this factor equal to 0. So again, let's draw these on the number line here, see how we can write this in interval notation. This time I'll put negative 3 and 4 on the number line. And both of those I'll put in open circle to show we can't have x equaling either one of those values. But those are the only two restrictions, right? X could be anything else other than those two specific values, so that means we would shade everything else on the number line. Here, negative infinity between negative 3 and 4 in the middle, and over to the right of 4, all the way to infinity. But this time, notice we've got 3 distinct intervals here. So right, using interval notation, we're going to go from left to right, lowest to highest. So this time it goes all the way left, so that's to negative infinity. Remember, always use parentheses on infinity and negative infinity. To negative 3 is where it stops, with a parentheses, because we're not including negative 3. That's a union, okay, with negative 3 with the parentheses, to 4 with the parentheses, since neither one of those are included. Union, or sometimes you put commas, with 4, parentheses, all the way to infinity. All right, let's take a look at another example here. This one, we've got h of x equals natural log of 3 minus x. One thing I forgot to point out on the other one, sometimes people wonder about. Notice this x plus 1 on the numerator, I didn't do anything with that because it wasn't inside a radical like the other one, like f of x. And there aren't restrictions on what a numerator can equal if there's no radical there. This could equal anything. So that's why it had no effect on the domain whatsoever, x plus 1. All right, now the next one, there's no denominators, there's no even radicals, even root radicals, but there is a logarithm. Remember, natural log is the same as log base e. Well, this is the logarithm we'll be dealing with most in AP calculus. Log base e, where e is approximately 2.71. Okay. It's a constant. So, remember with logarithms, what's inside the logarithm, in this case 3 minus x, so we saw here, it has to be not greater than or equal to 0, but just greater than 0. It has to be a positive number. So if you solve this one, there's a couple ways to do that. If you subtract the 3, you get negative x greater than negative 3. But then when you divide by negative 1, remember whenever you take an inequality and multiply or divide by a negative number, you have to flip the sign to keep it a true statement. So x would be less than negative 3 divided by negative 1 is 3. X has to be less than 3. And you can see that that makes sense logically here. Because if x is less than 3, then you're going to get a positive number when you plug it in. So on this one, you can draw this integral lines fairly easy. Less than 3. Nothing equal to it, so open circle and then less than 3 going this way. So this would just be one interval for our domain. Start at negative infinity and stop at 3. All right, and let's take a look at one last one. For j of x, we've got x plus 2 over the square root of 9x squared minus 4. So we've got two different things happening on the denominator. We know denominators can't be 0. But we also know expressions inside radicals have to be greater than or equal to 0. So if this square root of 9x squared minus 4 was not on a denominator, then all we would do is set 9x squared minus 4 greater than or equal to 0 if it wasn't on the denominator. But because it's on the denominator, we know in addition to having to be greater than or equal to 0, it also cannot equal 0. So what I'm going to do is erase the or equal to. Because it's on the denominator, it can't equal 0, it can only be greater than 0. If it equals 0, then we have to divide by 0, which we can't do. And then you can factor this one. You can see this, you can use difference of perfect squares factoring. What squared gives you 9x squared? That would be 3x. So 3x goes first in both of these. What squared gives you 4? That would be 2. One's minus, one's plus. And then if you set these equal to 0, 3x minus 2 equal to 0. Notice I didn't say greater than 0. We talked about this before. Because these are in factored form, greater than 0, these do not both have to be greater than 0. That is a false statement. They could both be greater than 0. They could both be positive numbers, but they could also both be negative numbers. Two negatives multiplied together to be positive. So by saying they're both greater than 0, that is not logically true. Okay? So I'm just trying to figure out what makes them equal to 0. And when you solve this one, you add the 2, divide by 3, you get x equals 2/3. Solve this one, subtract the 2 divided by 3, you get x equals negative 2/3. So let's put those two on our number line. I'm just going to draw it right up here, since I'm running out of room. At the bottom there. I'll draw the number line right up here and put down negative 2/3 and 2/3 on the number line. And we know it has to be greater than 0, not equal to. So these are the two places where it make it equal to 0, right? One of these 0 is multiplied by 0. So that means you're going to have open circles here. If it had to equal to, then we would have closed circles. And then we just have to test on our number line to see if the number on each of these makes a positive or negative. So what can we test over here that's less than negative 2/3? Well, lots of choices, negative 1, negative 2, negative 3, I'll just use negative 1. And the factor form is typically the easiest form to test to see if it's positive or negative. So you plug in negative 1 for x here, minus times 3 is negative 3 minus 2 is a negative number. Negative 1 times 3 is negative 3 plus 2 is a negative number also. A negative times a negative gives you a positive number. So we know it's positive there. Then between negative 2/3 and 2/3, probably the easiest number to test would be 0. So if you substitute in 0 for x here, 0 minus 2 gives you a negative number. It's still negative. Plug in 0 times 3, 0 plus 2 is a positive number. A negative times a positive is negative. Then here we can test something greater than 2/3, like 1, 2, and things like that. We plug in 1 times 3 is 3, minus 2 is positive. 1 times 3 is 3, plus 2 is positive. Positive times positive is positive. And then to see where we should shade, where it's negative or where it's positive, look back at your inequality sign to see what this means. We're looking for where this is greater than 0. In other words, where is it positive, right? So that means we shade the regions that we discovered it's positive to make this positive. Over here, to the left of negative 2/3, and over here to the right of positive 2/3. And then I'll write down the final answer here below. 2 separate intervals, so we've got from negative infinity all the way to negative 2/3 with a parentheses because it's not included. And then union that, another interval is 2/3, not included with parentheses, to positive. All right, let's take a look at something else about functions that we briefly talked about before, and that's inverse functions. So let's look at these in a little more detail. Remember, the notation we use to represent inverse functions looks like an exponent, but it's not. It's written up high like this. So the way to say this is the inverse of f, used to represent the inverse of the function f of x. So let's look at some different properties of inverse functions, then we'll look at how to find inverse functions. So if you have an inverse function inside the original function, they reverse each other. So they essentially cancel out. So whatever you plug in there into the inverse and then plug that back to the original function, you get what you started with. Same thing on this one. You have the original function on the inside, you plug in some x value there, and take that result, plug it in the inverse, you get back x. So that's one way of saying the inverses, they essentially cancel each other out. And since the inverse functions, remember the x's and y's are switched, and the domain is all the x's, and the range is all the y's, the domain of f of x becomes the range of the inverse of f. And similarly, the range or the y values of f of x become the domain or x values of the inverse. And we looked at this also briefly here. Because the x and y's are switched, it reverses the original function. The third property here is that if f contains some point AB on it, then its inverse must contain the point with the reverse coordinates be A versus AB, or x and y are switched. And because of that, graphically what you'll see is inverse functions are symmetrical about the line y equals x. So remember, y equals x is just a linear equation with a slope of 1 and a y-intercept of 0 at a 45-degree angle like that. So inverse functions you'll see are symmetrical about this because if you switch x and y, this function would stay the same. Everything else would be reflected across this line. All right, now to see if a function has an inverse, okay, what you look at is if the function is strictly monotonic. And I'm going to get a new term for you. We'll come back to it later in your calculus. In its entire domain. What that basically means is it's either always increasing or always decreasing. If it is, then it will have an inverse function. If not, then it will have an inverse, but its inverse won't be a function. The other way to tell graphically is like we do with, to see if something's a function, use the horizontal line test though instead of vertical test. And to have an inverse function, it's a function. The function must not cross any horizontal line you could draw more than one time. Okay? And what that means is it's 1-to-1 for every y value. There's one and only one corresponding x value. Then the steps for finding inverse, which we're going to go through right now. You first let f of x equal y. It's usually a little easier to work with in that notation. And you switch x and y variables, and that's what the inverse does. And you solve for y, and then you just rewrite it using the function notation. So let's look at some examples here where we can do that. So find the inverse of each function. All right, so let's first replace the y, so f of x with y, so y equals 3x plus 2 over x minus 5. Then the inverse switches the x's and y. So wherever there's an x, you replace it with y. Wherever there's a y, you replace it with x. You get x equals 3y plus 2 over y minus 5. Now this one might be the trickiest of all in some ways to find the inverse. Because once you switch the x's and y's, you want to solve for y. But notice we've got a y in the numerator and the denominator, so we need to deal with that somehow. Well, let's first try to get rid of the fraction. Multiply both sides of the equation by y minus 5. So times x, so we'll have on this side x times y minus 5. And this side the y minus 5 is reduced out. Be just 1, so all that's left on this side is 3y plus 2. Now we don't have any fractions. We still have this problem with more than one y term we're trying to solve for. So now if you just distribute out the x here, you get xy minus 5x plus 3y plus 2. And now the way you resolve this is, in more than one y term, get all the y's on one side, all the terms without y on the other side. So I'm going to subtract, actually I'm going to move that here so you can see a little better. Subtract the 3y over to this side, so we'll have xy minus 3y. And add the 5x to this side, so we'll have 5x plus 2 on this side. And what that allows you to do by getting all the y terms on one side, all of the terms that don't have y on the other side, is you can factor out the y like a GCF. And then we're left with x minus 3. And then all you have to do is divide by that x minus 3 to isolate the y. So y would equal 5x plus 2 divided by x minus 3. And the final thing to do is put it in inverse function notation. The original function was f of x here, so our inverse would be written like this. The inverse of f equals 5x plus 2 over x minus 3. All right, let's take a look at another one here. G of x equals the square root of x squared minus 1. All right, so let's first g of x is y, so this would just be y equals the square root of x squared minus 1. And again, remember the inverse function reverses the original function, so let's switch the x's and y's, so this becomes x equals the square root of y squared minus 1. And then we want to solve this for y, so get rid of the square root, square both sides. So that'll give us x squared equals the squared and squared cancel out here, y squared minus 1. Then add the 1, so get x squared plus 1 equals y squared. And then to get rid of that squared, you would take the square root of both sides. Square root of x squared plus 1. Be careful, those are two different terms there. You can't just take the square root of them separately when they're added and subtracted. Equals the square root of y squared is y. But do you see something important that I forgot there? Whenever you take the even root of both sides, remember you need plus or minus. And this is where we run into a problem here. This is the inverse of this function, right? But it's not a function. It's the inverse, but it's not a function. The reason why is because of that plus or minus sign. For instance, if you plug in one x value, let's say you plug in 0. You just get the square root of 1, but you get positive 1 and negative 1. And remember, to be a function, for each independent variable, like x you plug in, you can only get one y value out. Here, when you plug in 0, you get two different y values. So it's not a function, it wouldn't pass the vertical line test. So Because of that, can't write it in function notation. The inverse is not a function. All right, let's take a look at a couple more. This one's h of x equals the natural log of x plus 5. So the first thing to remember here is you can replace h of x with a y. And then it's important to remember what natural log is short for. Remember, it's short for log base e. So this is the same as y equals log base e x plus 5. And then don't forget we have to switch the x's and y's. That becomes x equals log base e of y plus 5. And then we need to solve it for y. And the right way to do that is to switch it out of log form into exponential form. The way you do that, the base you can see is e. Remember, the logs are equal to exponents. So whatever's on the other side of the equation of the log, in this case x, becomes your exponent. So e to the x. And that equals what's inside the log, in this case y plus 5. And then, to finish solving it for y, you just subtract the 5. You get y equals e to the x minus 5. Make sure you write that 5 down low so it doesn't look like it's up in the exponent. And this one, since our original function was h of x, we'll write as inverse of h equals e to the x minus 5. So we got one last one, j of x equals 2 e to the x plus 4. So again, we can replace j of x with y. Notice the x and the plus 4 are both in the exponent. And again, just find the inverse, switch the x's and y. So y becomes x becomes y. This time, we run into kind of the opposite problem we had in the previous problem, where we had y inside the log. This time we're trying to solve for y, but y is up in the exponent. So when that's the case, you actually do the reverse. You switch it into log form. But before we can do that, we've got this 2 here times the e to the y plus 4. So before we can switch to log form, since that e to the y plus 4 is not isolated, you first need to divide by 2 actually. So we get x over 2 equals 2 to the y plus 4. Yeah, sorry, not 2. E to the y plus 4. Not the wrong thing, sorry about that. So we get e to the y plus 4. And now switch it to log form. So in log form, that would be the log, the base is e. What goes inside the log is x over 2. And that equals the exponent y plus 4. The log always equals the exponent. And then last step to solve for y, you just subtract the 4. And usually that negative 4 will be written out in front. So negative 4 plus, and then log base e, you can write as natural log. Same thing, x over 2 equals y. And then the original function was j of x, so we can write inverse is written like this. The inverse of j of x equals negative 4 plus the natural log x over 2. And that concludes the notes for AP Calculus on the topic of functions.